Okay, we were discussing about the prodrug, and last class we have seen prodrug, that is definition. So, any compound prodrug means that is any compound which undergoes the biotransformation, and that is before showing the pharmacological. So that is a definition of the broader definition, and then we have seen the another definition, that is here. So the chemical another definition we have seen that is another chemical modification. Okay, and that is intentional chemical modification. If that is where chemical modification of biological active compounds to form new compound upon in vivo enzymatic action. Okay, so that will liberate the. That's what we have seen, two definitions. So one definition is biotransformation, and that was unintended, which is very broad. Okay, and another one is that the limited one, where the definition says that it is a chemical modification which we do intentionally. Okay, and then once we do the chemical modification and after administration and enzymatically you get back your parent molecule, that is intended modification. And why we have to go for the prodrug design, prodrug approach, why we have to convert an active molecule in active molecule, then administer it, and then again it will be converting back to parent molecule. So because these are the deficiencies, sometimes the molecule may have these deficiencies, parent molecules. To overcome all these deficiencies, so we have an approach, that is prodrug approach. So we have seen the main classes of prodrugs. So one is a carrier prodrug, another one is bioprecursor prodrug. So carrier prodrug also we have discussed. And in the carrier prodrugs, we will have a carrier moiety, and this carrier moiety generally it imparts lipophilicity to the parent molecule. Carrier molecule is attached to a carrier moiety is attached to a parent drug molecule, active drug molecule, through some functional groups, and then once if it is administered, again it will liberate the parent molecule. So here you will have a carrier moiety. Okay, so this carrier moiety will be attached to your active drug molecule. Then the principle of this also we have discussed, carrier drug, that is drug molecule, and then you attach a temporary moiety, transport moiety you can call, or carrier moiety, and then you synthesize these two together and you have the prodrug. This prodrug, it is a covalent linkage or temporary linkage only, which has to be easily hydrolyzable, which has to be easily cleaved. Okay, and the example we have taken, that is beta-lactam antibiotic. Beta-lactam antibiotic, we see that it's a broad spectrum antibiotic, and then compared to the bioavailability, if you see, of intramuscular injection of beta-lactam antibiotic and oral bioavailability, if you see, approximately only 40% of the drug drug is absorbed, oral bioavailability will be there, okay, compared to the intramuscular injection. So the reason is that here, if you see that, okay, that is and one more thing we have also, that is you cannot go on to increase the bioavailability, you cannot go on giving the dose increase. Okay, so that may destroy the intestinal flora. So for that reason, what has been done is that here, this is your ampicillin, and this ampicillin was converted into prodrug moiety, prodrug. So, and another one also, here you have the another prodrug. Okay, so one is pivampicillin, another one is becampicillin. Pivampicillin, becampicillin. This is a pivolyl acid, and this is again a formaldehyde. Okay, so here what happens is that prodrug, okay, So here ampicillin, if you see, it is having very less lipid solubility, and to make it more lipid soluble, if it is less lipid soluble, so why it cannot cross the intestinal, intestine and enter into the systemic circulation. If you see this is a water soluble compound, and orally if we give this molecule, so we have seen that it is only 40% is absorbed. If you give 100 milligrams, then only 40 milligrams will be absorbed. Remaining 60 milligrams will be excreted. That is going as waste, and it will not show much efficacy also. Out of 100 mg, only 40 mg reaching the target. We cannot say also it is targeting, but availability is 40%. And that is because of the low lipid solubility. If you have a proper optimal lipid solubility, it can cross lipid bilayer of intestinal wall and enter into the systemic circulation. So to increase the lipid solubility, what we have done is that we converted this molecule into a prodrug molecule. This is active molecule, and this we converted that into a prodrug molecule. One is pivampicillin. This is pivolyl acid, pivampicillin, and another one is becampicillin, and these two are the prodrugs. So, and these ester moieties, what they do is that they can increase the lipid solubility, and once if it is and you will have the proper absorption through the intestinal wall, and then they can cross the intestinal wall, and bioavailability will be increased. And here this is how it undergoes the to liberate the parent molecule. This is parent molecule, and we converted this into prodrug, and the prodrug is more lipid soluble compared to the parent molecule, and then it undergoes the degradation, pivolyl acid and formaldehyde. This is aldehyde, formaldehyde, and then you have this is acetaldehyde. This is becampicillin. It undergoes the degradation, that is, and then you will get back the parent molecule, and you have carbon dioxide and acetaldehyde and ethanol. And these two again, why I have given is that, so when same, it is in both cases, it is ampicillin only. But this, if you see that these two metabolites are not common in the you find in the human body. These two metabolites, these two compounds or the pro-moieties are not common to the human body. And if you see becampicillin, this is much more tolerant also, and because you see that carbon dioxide, it is common in our body, acetaldehyde, this is common in our body, ethanol. So ethanol, it is not common in our body, but our body can recognize ethanol, alcohol, those who consume the alcohol. So our body can recognize it, then you have the effective mechanism to detoxification. So this also can be detoxified immediately, it can be eliminated from the body, and carbon dioxide also immediately, we know that how it will be eliminated from the body, and this also, ethanol also can be eliminated from the body. But in these two cases, if you see, this is not a common substrate for our body. So that's why compared to this, so both are having lipid solubility. This is also given. It is not that it is not given. This is also given, and this is also is given, administered, and both these two are prodrugs, and which will liberate the active, that is a parent molecule, inactive to active one through the biotransformation through mainly hydrolytic reactions. So it is an ester moiety. It can easily undergo the hydrolysis. Esterases are there, hydrolysis are there. So those enzymes, they will convert this into liberate the parent molecule. But these two, one is pivampicillin, another one is becampicillin. So compared to this pivampicillin, becampicillin is much more tolerated, because whatever or the metabolites we have after cleaving off, after liberating the parent molecule, we have the common products, that is, which are common to the human body, but these two are not. So now after converting here ampicillin into prodrug, what happened is that absorption almost increased to 98%, 98 and 99%. So you see that where it was 40% and it has come down, it increased to 98% with the ampicillin and becampicillin. So, and the generation of within 15 minutes, you will get back the parent molecule, ampicillin in the bloodstream through the hydrolysis. So then the released carrier molecules, as already I have told you. Okay, so that is ampicillin. The ampicillin is a ampicillin is a trimethyl acetic acid. Okay, pivolyl acid. I told you that, and then the common products in becampicillin also we have seen, that is acetaldehyde and ethanol, carbon dioxide in both cases. So this is what happened. 98% bioavailability has come to ampicillin and 99% to becampicillin. And then next thing, if you see that there is another thing. So here the dose which was given 2 grams has come down to 0.81 grams. 0.81 grams, that is a dose, daily dose. So from 2 grams to it has come down to be 0.81 grams. So this is what happened with the prodrug conversion. Active molecule is there, which is active, but its bioavailability was less, and the bioavailability was less because of its low lipid solubility. And to overcome that, okay, lipid solubility, bioavailability problems, also shortcomings, what we have done is that we try to increase the lipid solubility of the ampicillin, and that is by adding some ester moiety. And then once you do that, bioavailability increase to this percentage, and then the doses also we can reduce from 2 grams to 0.81 gram, almost 800 milligrams. So 120 milligrams are reduced. This is what happened in the when we deal with the ampicillin we go for. Okay. So next, what are the here the types of moieties you can convert. Okay, you can convert into pro-moieties. So there are various functional groups, okay, which you can, what type of functional groups are there and how you convert them into pro-moieties. You have to be very selective, and the selecting of the pro-moieties also very important. Okay, that is because the pro-moieties should be easily cleaved off. Okay, and this pro-moiety also should not be toxic to the humans. So in that way, what are in a drug molecule, what are the functional groups you can select the drug molecule to convert into prodrug? So here first one is that alcohol functional groups. In a drug molecule, if you have a alcohol functional group, okay, so or phenolic functional group, so that you can convert them into pro-moiety. So here if you see that epinephrine, okay, epinephrine, it cannot cross the cornea, okay, and because of the lipid again further it is solubility, cornea it cannot cross, which is used in the glaucoma, this epinephrine. Okay, so red part whichever it is shown that is the pro-moieties, that is later on added. Okay, so pivolyl acid it is added, pivoleic acid, this is one, two. Otherwise you will have, instead of these moieties, you will have the, here this is hydroxyl group and this is also hydroxyl group. So of these two hydroxyl groups, hydrogen is replaced by the pro-moiety. Okay, here one hydrogen is replaced with the pro-moiety, and here also one of the hydrogen is replaced with the pro-moiety. So, and as such, if you give only epinephrine, it cannot cross the cornea. And then what you do is that, since it is having hydroxyl groups, so these are hydroxyl groups, we are talking about the which are the functional groups are there in the drug molecule and how we convert them into prodrugs. Suppose in a drug molecule, if you have alcoholic functional groups or phenolic functional groups, how you convert them? So by simply, and this conversion generally increase the liposolubility, and with hydroxyl groups or phenolic group, we go for the esterification. Okay, and with the carboxylic acid, since alcohol is there, then we go for the esterification. For example, you have a epinephrine is having, and it is highly water soluble. Okay, it is water soluble, and because of these hydroxyl groups, it is water soluble, and in cornea it cannot cross. So these hydroxyl groups are masked, are converted into pro-moiety. So this is also where pro-moiety is added, and this functional group, if you see that, it is an ester. So with the hydroxyl groups, if you have in a molecule, so probable functionalization is esterification. You can do this is one of the probable esterification. You can probable route to convert the drug molecule into prodrug molecule. So through esterification of alcohols, you can convert the drug molecule into prodrug. Okay, so this is one types of Moieties used for the various functional groups. So now, what are the Moieties we are using here? Moiety, that is carboxylic acid as a Moiety. If you have what alcohol or phenolic hydroxyl groups. So in epinephrine, we have here one hydroxyl group, and here we have an hydroxyl group, and this hydroxyl group, to that we can add carboxylic acid and convert the hydroxyl group into ester functional group, and this increases the lipid solubility. This is one case. So here in this example, you have a hydroxyl groups, and if you have hydroxyl groups, what are the Moieties we can use, and to which functional groups we can convert them. So here we have hydroxyl group. Hydroxyl group can be converted into ester functional group. Okay, so this is an example. You have epinephrine. So, and epinephrine, the problem is that it cannot cross the cornea, and so absorbed. And so for here we are using pro group, that is Moiety, make it as ester, and it can lipid solubility is increased, and it can cross through the cornea, and you can treat the glaucoma. So then next one is derivatization of, okay, so derivatization of aldehydes and ketones. If we have aldehydes and ketones in the functional, okay, if you have a aldehydes and ketones in the your drug molecule. So this is hydrocortisone, this is a drug molecule, and here we have a ketone functional group. Like this functional group is there, means how do you convert into prodrug? Okay, what is the strategy? So one, you can go for that ethylene diketal. This is one thing you can do. This is how you convert ketone into Moiety. Or third one is that you can go for the spirothiazolidinones. This is spirothiazolidinone, and another one is that you convert that into, if you have a ketone functional group, you convert that into oximes, acetylated oximes or whatever oximes you can. So these are the three ways. If you have a ketone functional group in your drug molecule, okay, ketone functional group, if you have a drug molecule, then you can convert that into ethylene diketal. This is ethylene diketal. You can convert that into, okay, Moiety, and or otherwise spirothiazolidine. You can convert the spirothiazolidine, or then you can convert that into oximes. You can convert into oxime ketone functional group. You can convert into this functional group. You can convert into oximes. Oxygen we replaced here with the nitrogen. Replace with the nitrogen. Okay, and here I have given the example, that is hydrocortisone, which is an anti-inflammatory drug, and this drug is converted into, see that it is a spirothiazolidine derivative, and a series of reactions you will get back your, okay, parent molecule. So this parent molecule, hydrogen, is converted into, which is having a ketone functional group, that was converted into spirothiazolidine. Here you have the spirothiazolidine, and then with the series of reactions, okay, in vivo, it will be converted into parent molecule. And this conversion, what it does is that it improved the topical anti-inflammatory activity. Topical anti-inflammatory means, that is, if you have inflammation on the skin. So inflammation on the skin, if you have, and hydrocortisone, topical anti-inflammatory activity was increased. Okay, so that's what here the advantage, converting the hydrocortisone into its Moiety. This is how, if you have in your drug molecule, if any other, some of the kinetic problems associated, and if you have aldehydes and ketones, and then these functional groups, this way you can convert. Either you make it as a diketal, that is ethylene diketal, or you make it as a spirothiazolidine, or you make it as a oxime. So these can improve the solubility properties with the ketones if you have a drug molecule. So this is how we, that in derivatization of aldehydes and ketones. So first, what are the probabilities you can use, okay, for if depending on the functional groups present in your drug molecule. In my drug molecule, if I have hydroxyl groups, then what I have to do with the hydroxyl group to convert into promoiety. So you can hydroxyl groups you can convert into esters, that we can. Example, epinephrine. So epinephrine, its lipid solubility can be converted into esterification, and which we can use the cornea. And then if you have aldehydes, and that is ketone functional group, aldehyde functional groups in your drug molecule, how you convert that into what are the promieties you can convert? Prodrugs you can, okay, how to make the prodrug? Ketone functional group if you have, you can convert into diketyl or ethylene diketyl or spirothiazolidine, okay, and then oximes, okay, especially stylated, okay. So these oximes you can later on this series of reactions, only one example I have given, series of reactions you can get back the your parent molecule. Then derivatization of drugs containing carboxylic acids. If your drug molecule is having carboxylic group, so hydroxyl functional group also is there here, but this is the levodopa, which is used in the Parkinson's disease, that is a nerve degeneration disease. So in Parkinson's CNS disease, where you will have the degeneration of nerves. So to treat the Parkinson's disease, we'll use the levodopa, and later on it will be levodopa will be converted into dopamine, okay, and dopamine. So we use in the treatment of Parkinson's disease. But levodopa, if you see here, so it undergoes the extensive metabolism, that is first pass metabolism. You might have studied that first pass metabolism. Levodopa, the problem associated with the levodopa, you administer it once it enters into systemic circulation or liver. The liver, it undergoes the extensive metabolism, and levodopa may not even reach the CNS. So, and it is a, and one more property also, this hydroxyl group is there, and carboxyl group also is there in levodopa. So, and that will be hydrophilic. It cannot cross the blood-brain barrier. So then what I do is that since hydroxyl group here, carboxyl group is present, and levodopa, I converted into ethyl ester of levodopa, and this is a prodrug. So this increase the lipophilicity, and it can cross the blood-brain barrier, and you can treat the Parkinson's disease. Here you see that carboxylic group is converted into ester functional group. Okay, ester functional group. Even if you have here hydroxyl group is there, that we converted into a prodrug by using an acid, and here we have an acid function group. If you have acid function group, and the drug molecule, parent molecule, if it is having any kinetic deficiencies, either lipid solubility, or if it undergoes very easily metabolic reactions, okay, and then this acid functional group you can convert, okay, into ester functional group. Now this is a prodrug. You convert this active moiety into prodrug moiety, inactive moiety, and then simply it can be cleaved off because hydrolyses are there, esterases are there. So those enzymes will act easily. This molecule can be cleaved off, and you'll get back your your parent molecule. Okay, and esterification, you know that increase in the number of carbon atoms increases the lipophilicity. I have added 2 carbons here. So increase in the number of carbons, so increase the lipid solubility. So this is, if you have carboxylic acid, how do you go for the prodrug design? So this is how one method is this. And next one is that in a drug molecule, if you have amines, okay, if you have amines, how you go for the prodrug conversion? So here you see that gabapentane, okay, it is having a amine functional group, which is gabapentane is used as a anticonvulsant, and that we converted into, okay, the anticonvulsant, and it is a CNS drug, right? Anticonvulsant CNS drug, and that we converted into again amides. Okay, it is not a simple amide. Okay, one more thing you're telling. It is an activated amide. Activated amide means here, so we will not stabilize the amine here. Okay, we will not be resonance stabilized it. So normal amide means through this. Okay, through this carbonyl functional group, it will be stabilized, so bond cannot be cleaved. And that's what normal amide. But here it is an activated amide. Activated amide means this carbonyl functional group and this amine will not be resonance stabilized, because we have the next to that you have the oxygen. Okay, next we have the oxygen. So this oxygen will not allow resonance stabilization of this amine and ox carbonyl group, and so that it can be evenly cleaved. If this oxygen is not there, okay, you understand my point here. If this oxygen is not there, this bond cannot be cleaved because it will be resonance stabilized. Since oxygen is there and it will not be resonance stabilized, and bond can be easily cleaved enough, and you will get back the. And again here, why we have done this is again lipophilicity. So increasing the lipophilicity, we are trying to increase the lipophilicity by converting the amine functional group. If you have amine in your drug molecule, you can convert that into amides, okay, or you can add peptides, okay, or you can add imines, C double bond N, or you can convert them into quaternary ammonium salts. Simply you can convert them into quaternary ammonium salts. So here I am giving the example, that is how you convert amines to activated amides. So only one example. All these examples we are not going to deal with that. So activated amides, I converted GABA pentane, which is anticonvulsant drug, and this is a horizont of this molecule, where amine is converted into amide, activated amide. So here normally the why we have converted that gabapentane, so the oral bioavailability of gabapentane is not a dose dependent. Okay, so this you remember, the oral bioavailability of gabapentane, it is not a dose dependent. That means bioavailability sometimes you can increase by increasing the dose, but in case of gabapentane, here the bioavailability is not based on the dose, okay, because due to the saturation of its absorption pathway through a low capacity amino acid transporter localized in the upper small intestine. So here we have a protein, okay, low capacity amino acid transporter. Okay, we have a protein that transports low capacity amino acid transporter. So this transporter, it transports the amino acids through the that is upper intestinal wall, and here it becomes so much saturated, so it cannot be gabapentin. Okay, so this protein low capacity amino acid transporter, it gets saturated, okay, and then it can, because their expressions may be less, their number may, these transporters may be less, okay, and transporters are less, and then but your when transporters are less, then plasma exposure to the gabapentin patients is also unpredictable. Okay, so here you are giving a dose, but that dose is unable to cross the from intestine to the systemic circulation. So, and here that is happening because of the here because of the low capacity of amino acid transporter. So these amino acid transporters are low capacity, they have very low capacity to transport this gabapentin. That's why we will not, this is predictable, sometimes may be increasing, sometimes may be reducing depending upon that. Okay, so that's why we have a carbamate prodrug. So here carbamate and designed and actively absorbed from the intestine. So what I did is that, okay, so amine is converted into carbamate. Okay, see here NHC double bond O, and this is, we call it as a carbamate. It is similar to the ester. Okay, similar to the ester. Amine is converted into carbamate, and then that will be easily absorbed through the intestine. And then this is a stable again, and it can be easily converted into gabapentin. Okay, and then it will be converted in gabapentin will be liberated, and you will have the other moieties, isobutyrate and acetaldehyde and CO2, and the oral bioavailability of the prodrug almost increased to 94%. So if you have amines in your drug molecule and it is having certain kinetic problem, that is absorption or transportation, And what we do is that with these amine groups, we can convert into activated amides, or you can convert them into peptides or imines or soft quaternary ammonium salts. So example, you have the gabapentin. Gabapentin, where it is converted into activated amides, that is, we converted that into carbamate. Okay, oh, and activated amides. And then with that, what happened is that 94% of bioavailability came down to. So why the oral bioavailability of the gabapentin is less? Because saturation of low capacity amino acid transporters. Amino acid transporters or the transporters which transfer gabapentin from intestine to systemic circulation. This is a amino acid transporter is a transporter which transports gabapentin into the systemic circulation. So this transporter becomes very easily saturated. Okay, so the further it cannot transport. So that's why what we did is that we converted gabapentin into carbamate, and carbamate is lipophilic, and then it can easily cross the lipid bilayer and enter into the systemic circulation and increase the bioavailability to 94%. So this is how you can do if you have amine groups in the drug molecule, and amine group, how it can be converted into prodrug. Okay, and if you have, next one is that derivatization of amides. Suppose if you have amides, okay, amides in the amide functional group in your drug molecule, how it is amidins. Okay, amidin means this one. Okay, amidin functional group. Okay, amidin. So these are derived from the oxoic acids, amidin functional group. So C double bond NH and NH2. So amidin functional group. Sometimes you will call it as a guanidine functional group also. This one, and these amidins. If you have these amidins in your drug molecule, how you do it, and this is how we do amidin functional group. So you can convert, hydroxylate it, or you can do it as a ester functional group. You can make it as an here. You can add an ester functional group here. You can see that acetylation or whatever it may be. And here, this example, if you see that we have an amidin functional group here also, and amidin functional group. What we have done is that this is the actual prodrug molecule. Okay, prodrug, and this is a milagatron. Milagatron is a prodrug molecule, that is active molecule, which is an anticoagulant, but it is not lipophilic, and because of this moieties, all are hydrophilic moieties. Okay, all are this one and this one, all are hydrophilic moieties, and I have an amidin, and this is double prodrug. Okay, one more thing. Okay, this is here you can see that milagatron, which is not lipophilic. Okay, we converted into ximilagatron is an anticoagulant simply by hydroxylation that you can convert imidine. Okay, this is if you have this, and then next one is that this is how you do it if you have amidins. And next one is that prodrugs for compounds with acidic NH functional group, and here it is a 5-fluorouracil, and how you convert them into again increase the lipid solubility here. Okay, and you can see that here acidic nitrogen is there, where this is a prodrug actually without this red moiety, and here you will have a H. Okay, that H can be, so like here you have H, right? Here also you have the hydrogen, and you can convert that into this by increasing, that is, you can convert into prodrug moiety, okay, prodrug molecule. Okay, so or you can make them as sulfonamides. If you have NH functional group, you can make them, that is sulfonamides. You have seen that how we have done with the sulfonamides. You can convert them into carboxamides. Okay, or you can convert them into carbamates. We have seen the carbamates, and you can and other and other NH acidic compounds can be acetylated, okay, or converted into phthalidide derivatives. So this is how the approaches we have, depending upon the functional group present in the our drug molecule. We have various approaches to convert them into prodrug molecule. If you in your drug molecule you have an hydroxyl molecule, how to convert that into prodrug molecule. If you have a carboxylic acid, how to convert that into pro molecule. If you have a amine, that is amine, you how to convert them. If you have amides, how to convert them. And if you have NH functional group which is acidic, how to convert them. Okay, so this is how we convert based on the functional group present in the R drug molecule. We can convert them into prodrug molecule, and we have to choose this pro moiety. It is not a trial and error, right? Based on the functional group. Okay, so here we have amidine, so simply here we have amidine, that simply we convert it into hydroxyl group. So this we have to choose it. Okay, this we call it, we call it as a pro moiety. So based on the functional group present in your active, that is parent molecule, you have to choose the pro moiety. So how to choose the pro moieties? So if you have hydroxyl group, what pro moiety you have to add? If you have carboxyl group, what pro moiety you have to add? If you have amine function group, what pro moiety you have to add? If you have amidine, what pro moiety you have to add? And if you have amine, that is which is NH, which is acidic, so that means which can liberate the hydrogen, which can give off hydrogen. So then what are the pro moieties you have to add? So this is based on the functional group and selection of pro moieties, and convert active molecule into, that is prodrug, and overcome the either liposolubility, lipid solubility, or kind absorption or bioavailability to overcome all the problems. So today we'll start the class with this here, and we'll continue for the next, okay, continue in the next classes.